Hi everyone, in this video we're going to see how determinants can be used to compute areas and volumes in 2 and 3 dimensions. So let's start simple. We'll start in 2 dimensions and look at a special case. Now I have these 2 generic vectors here, and I want to look at a restricted case where the second component of the first vector is equal to 0 and the first component of the second vector is equal to 0. Let's draw the picture. Okay, so here I've drawn u and v, and maybe you can see why I wanted to use this special case. These 2 vectors lie along the coordinate axes. Now let's look at the parallelogram that's determined by these vectors. So to find it, I'm just going to take a copy of the blue vector v, move it over, and put it so the tail of the v vector is situated right at the tip of the u vector. And then I'm going to take a copy of the u vector and situate it so that its tail is at the tip of the v vector. This area that's inside here is the area of a rectangle because all of these are right angles. And the area of this rectangle is just u1 times v2. Now let's see where determinants are coming in. Well, if I make the matrix that has as its first column the vector u and as the second column the vector v, I get this. And if I compute the determinant of that matrix, remember the determinant of a 2 by 2 matrix we get by just multiplying along the forward and backwards diagonal and taking the difference. I'll get u1 times v2 minus 0 times 0, and that's just equal to u1 v2, which is exactly the same as the area that we got using the usual geometric formula for the area of a rectangle. Now let's look at a slightly more general case. So you see here I have the same 2 vectors. The only difference is that now I'm letting the first component of the second vector be non-zero. So let's see what the picture of that looks like. Here I've plotted the 2 vectors, and you can see that v is now allowed to point somewhere that's not on the vertical axis. Now what's the parallelogram that's determined by these 2 vectors? Well, again, I'm just going to take a copy of u and move it up so that its tail is situated at the tip of the vector v. And then I'll take a copy of the vector v and do the same thing. Now this is what my parallelogram looks like, and if I want to find the area of the parallelogram, you may remember back from Algebra 2, trig, or something back then, maybe even from when you were younger, that this area is equal to the base times the height of the parallelogram, and in this case it's easy to kind of read that off. The base has length u1, and the height of this is v2. And if you maybe are a little hazy on why, you can remember that that area of that triangle is the same as the area of this triangle. So you could just cut that part off, move it over, and then you would have a rectangle that is width u1 and height v2. Now let's see what we get when we compute the determinant in the same way that we did before. So this determinant is again u1 times v2, which again is the same as the area we got just using geometry. Now we can ask, is this true in general, or is it just true for these special cases where we have a rectangle or a sheared rectangle? Where we have a parallelogram that is situated so that one side of the parallelogram is on the axis. Well, it's actually true in general. So let's write down a theorem. And here it is. So the theorem says that if we have 2 vectors that are in 2 dimensions and we consider them to be defining the sides of a parallelogram, then the area of that parallelogram is going to be the absolute value of the determinant of the matrix that has as its columns those 2 vectors. Let's see an example. So we'll have 2 vectors, u equal to minus 1, 4, and v equal to minus 2, 2. And what's the picture look like? This. And I've obtained again the parallelogram by just making copies of those vectors and situating them in a tail-to-tip kind of way. And the area of this parallelogram is going to be equal to the absolute value of the determinant, just like the theorem says. So the value of the determinant is going to be -1 times -2, so that's 2, minus 2 times 4. So that's equal to -6. So the area is going to be equal to the absolute value of that determinant. So the area of this parallelogram is 6. Now that is something that I would not want to try to compute using geometry. Trying to figure out what the base and the height of that parallelogram might be kind of a pain in the neck. But this way was very easy. And maybe I'll just make my last comment about the sign of this determinant and why we need to take the absolute value. It's kind of like how when you're trying to calculate the area under a curve in calculus, and part of the region that is supposed to be included in your area calculation sits below the horizontal axis. In that case, you know, if you just do the integral, it'll turn out to be a negative number. So you take the absolute value of that integral. It's the same kind of thing happening here, except here it's about orientation. In these other examples, we had as our first column vector the green vector. And when we were finding the area, it was like we were rotating and sweeping the area through from the green vector to the blue vector. And in both of these cases, we were moving counterclockwise. In this case, that area that we're finding is one that we get when we're moving clockwise. And so that's what makes the determinant negative here. If we swapped these columns so that we were starting with the blue vector and going to the green vector, it had 2 minus 2 here and -1, 4 over here, then we would have gotten +6 as the value for the determinant. Okay, so that's it for now, and in the next section we'll talk about finding volumes of parallelepipeds in 3 dimensions.